Okie dokie. So we're going to go ahead and do a couple things in this video. This is all about simple harmonic motion, and we're going to use Newton's second law to derive the period of a spring mass system, a simple pendulum, or a physical pendulum. So if you have not already, I would encourage you to watch my video called Newton's second law, simple harmonic motion. In that video, we derive the period of a spring mass system. Right now, we're just going to summarize that for spring and then go into a little bit more detail for a simple pendulum and physical pendulum. Okay, so again, if we have a good old spring, let's say it's oscillating on a horizontal surface, and there's a block of mass m attached to it. So let's say that's equals A. We have good old spring force pulling it backwards. We have normal force, and we have gravity. In this case, it's only accelerating in the x direction, so we're just going to look at F net x. So again, we say F net x equals negative force of spring because Fn and Fg are in the y direction. F net is ma. Spring force is negative kx. Again, spring force is a restoring force, which is why we have that negative sign in it. Again, we know acceleration is not constant. When the object is in equilibrium, acceleration is 0. When it's pulled back to, let's say, its amplitude, acceleration is going to be a max. So it's not constant, and it is going to be the second derivative of position with respect to time. So we have cool. This good stuff right here. Awesome. So we went ahead and we did some simplifying and solving. In a previous video, we went ahead and showed that k over m essentially represents omega squared. So whatever the coefficient is in front of the position x function is going to represent omega squared. So we know in this case, omega is going to be the square root of k over m. And let's go ahead and just finish this off and derive period of the spring. So period of a spring, and again, period for anything is just 2 pi over omega. But let's go ahead and plug in omega for a spring. So that's going to be 2 pi square root of k over m, which is going to be 2 pi root m over k. So again, that is a period for a spring. Okay, great. So now we're going to go ahead and use a similar strategy. And again, if you wanted more of a refresher on why omega squared equals k over m, watch that other video that I referenced. Cool. Now we're going to go ahead and chat about simple pendulums. Okay, so we're going to go ahead and do a similar process for simple pendulums. So let's go ahead and say I have a mass on a string. And again, this string is massless, which is the definition of a simple pendulum. It's some mass on a massless string or massless whatever, rotating back and forth. So let's say that is like if you were to drop a plumb line, that's like straight up and down vertically. And let's say it's oscillating to the right. So it's oscillating upwards. Let's go ahead and draw our free body diagram first. So we have force of gravity acting on it, which is just going to be mg. And we have force of tension. Cool. We have that good old thing. Okay. So now what I want you to think about, just because we're dealing with things rotating, I want you to think about what forces make this rotate. Okay. So if I have this mass on a string, if I apply a force directly inwards like this, directly like that towards the pivot point, tension is not going to make it rotate because that's in the same line as like the radius, which is like of length L, whatever that string is. While some part of gravity is going to make it rotate. Let's go ahead and think about what part of gravity is going to make it rotate. So this angle is theta. So let's see, this right here, if you pull down, let's say on your pencil, if I pull straight down on this mass of m, that's not going to make it rotate. But if I push perpendicular on it, that is going to make it rotate. So I'll call it Fg perpendicular will make it rotate. And Fg perpendicular is going to be mg sine of theta. Cool. So keep that in mind. Okay, so now since we're dealing with things rotating, instead of dealing with F net equals ma, we are going to deal with the rotational analog of that, which is going to be T net equals I alpha. So T net, let's think about what forces make it rotate. Again, the only force acting on it, tension doesn't make it rotate. Some component of gravity makes it rotate, Fg perpendicular. So we will have Fg perpendicular. So again, a torque is a force times distance from the pivot, and it is a distance L from the pivot. It is rotating, so gravity is pointing down and it's rotating the opposite direction. So I'm going to make this torque negative. Those are going opposite direction. I is the moment of inertia. Let's see. What is I in this case? I is going to be what? Actually, let's just wait till later to plug that in. Cool. So we have I, alpha. Again, alpha is going to change. That's the angular acceleration. It's going to change with the angle. So alpha is d squared theta dt squared. So I times d squared theta dt squared. Okay, let's go ahead and start plugging some things in. Cool. So FG perpendicular is mg sine of theta. So this is negative mg sine of theta times L equals I d squared theta dt squared. Cool. Cool. So now we have, I'm going to just rearrange this a little bit. It's mgl times sine of theta over I equals d squared theta dt squared. Okay. So now what we're going to use is we're going to use something called the small angle approximation. So with the small angle approximation, for any very, very small angles, and again, this is only true if things are measured in radians, so make sure you keep your good old calculator in radians. Sine of theta is approximately theta. And I encourage you, pull out your calculator and test it out. Like type in sine of, cool, like I typed in sine of 0.2, and that is 0.196. And 0.196 are almost the same thing. You could try it with different numbers, like what's sine of 1? Let's see what that is. Sine of 1 is, okay, not quite as close, because 1 is not a super small angle at all in terms of like radians if you're measuring that. So let's do another small one. Let's do sine of, let's say, 0.001. Let's see what we got there. Sine of 0.001. Oh my goodness, that's so small. So it's like 0.000999, which is basically rounded to 0.001. Cool. So again, this whole thing, this whole derivation only works for super small angles overall. Cool. And you could prove that with some fun curious things that you would do in any math, Calc AB or BC, probably BC Calc. Cool, so let's put that in. So we have MGL over I times theta equals d squared theta dt squared. Okay, so let's go ahead and look at our similarities. So d squared theta dt squared, that is just like our previous example. That is, if I can get to it, that's like d squared x dt squared. So we had a good old x in our previous one. Now x is theta, so it's essentially the angular equivalent of it, so that's theta. Whatever we have left out front, which this I circled, k over, there's a negative sign, which there is in this case, k over m was omega squared. So now our omega squared, this whole thing right here is going to be, let me just go off for it. So this whole thing right here is going to be omega squared. So we know omega squared equals mgl over I. So omega is just going to be square root of mgl over I. Awesome. So then let's go ahead and plug everything in. So we know period is 2 pi over omega, and in this case omega is square root of mgl over I. Let's see, I'll simplify that a little bit. So that's like 2 pi times what? I over mgl. I in this case, so this is I for a mass at the end of a rod. So I in this case is just going to be mr squared, which r is just ml squared. This is a point mass, 100%. So this is just 2 pi root ml squared over mgl. Oh my goodness, I love it when things cancel. A squared cancels with 1 down there. And then we get, sorry, that was a little messy, but period of, I'll call it a simple pendulum, SP, is 2 pi square root, oh, an m cancels out too, I almost missed that. Cool. 2 pi square root of L over G. Awesome. So that we just derived the period of a simple pendulum. And again, there are a lot of calculus things at play where y mgl over I is equal to omega squared. And again, I encourage you to watch that other video I referenced in case you have more questions on that. What I want to do is let's just compare that for a mass spring system, which we just previously talked about. So again, that's if you have a mass on a spring oscillating either horizontally or vertically. So I like to have these equations memorized. I think it's helpful to have them memorized they look almost identical. I want you to think about similarities. 2 pi and 2 pi is there. We have our square root and square root. In this case, I think of for a simple pendulum, gravity is the force that makes it rotate, which is related to acceleration due to gravity. While for a mass spring constant situation, a spring force is what makes it rotate, which is related to K. So I just remember like the G goes on the bottom, the K goes on the bottom, while it's L and M. Cool. So you have those two equations right now. So we're going to go ahead and now derive the equation using these same ideas for a physical pendulum. So now I want you to guess, what's the difference between a physical pendulum and a simple pendulum? I bet you guessed it. But a physical pendulum is where the whole object has mass, as opposed to just one point having mass. So what I think of is, let's say I have something rotating. Let's say it's a big blob right here, rotating. So this would be an example of a physical pendulum, because this is rotating back and forth about this whole point X right there. Okay, so for this object, I want you to think about, where's the center of mass going to be of this object? Well, closer to the massive side. So I'm going to go ahead and label that is going to be the center of mass, which again, we say the force of gravity is originating from the center of mass of that object. Another thing that we're going to come back to is D equals the distance from pivot to center of mass. So again, this thing is rotating, oscillating kind of side to side. So if it's rotating, it's not moving linearly back and forth in a linear fashion, it's rotating. We're going to use the same idea as the last step to derive the period of a physical pendulum. We're going to say T net equals I alpha. So again, I is I, alpha is d squared theta, dt squared. The net torque is negative whatever FG perpendicular is. So same pattern as previously. So if I say this is FG perpendicular, let's put that in the right color. So that's negative FG perpendicular. So a torque is a force times a radius, which in this case the radius is d. Cool. And force perpendicular is just negative FG, which I should say that's negative FG sine of theta. So that's FG sine of theta times distance d. Let's make sure we get that all in. Cool. So then that's negative mg. I'm going to move the d times what? Sine of theta. I just rearrange that a little bit. Times I d squared theta dt squared. We're going to go ahead and do the same process above. Sine of theta, we'll use that small angle approximation. This is approximately theta. Again, this is only true for small angles. So mgd times theta equals I d squared theta dt squared. Let's see. Rearrange things a little bit. So mgd over I times theta equals d squared theta dt squared. This coefficient, and again, there's more proof in other videos, is essentially omega. So essentially we say, so let mgd over I equals, sorry, that's not just omega, it's omega squared. So omega is going to be the square root of mgd over I. So again, if we do the final derivation period, so again, this is for a physical pendulum, is 2 pi over omega, and omega is square root of mgd over I. So that is going to be 2 pi square root of I over mgd. And that is the period of the physical pendulum. Cool. And that looks a little bit similar to the period of a simple pendulum, where again the whole, so I'll put this on the side. Simple pendulum is just 2 pi square root of LG. So there's some similarities. G is on the bottom for both of them. But for simple pendulum, we know what the moment inertia is, while physical pendulum, you'll have to plug it in. It'll be different for each situation. If you want to learn more about physical pendulums, I have another fun video, and we'll talk more about this in class soon, about physical pendulums. So feel free to check out that video. Awesome. Thanks so much for watching.